We still have, okay. So thank you everyone to come back from the break. We are going to continue with the side channel attacks. The first one is the pushing the limits of, do you have your slides already? Yeah, okay. So pushing the limits of generic side channel attacks on LWE based cams. And the speaker is Goku.
Hi all, my name is Gokulath Rajendran. I'm from NTU and I'm here to present our research work on side channel attacks. So basically we formulated a methodology to recover multiple secret coefficients in module LW based schemes. So we specifically target Kyber as it is recently recommended by NIST for standardization. So this work is jointly carried out by NTU Singapore and KU Leuven. So joining with me is our Prasna Ravi, Jan Peter, Shivam Bezin, and Anupam Chattopadhyay. So this is a summary of the presentation. So I'll start with the background, which is the literature that motivated us to carry out this research work. Then I'll present the novel parallel PZ Oracle attack that we are targeting here. Then I'll present detailing on the experimental research that we got from STM32F4 microcontroller. Okay, so here is the attacker model. This is under static key setting. So Alice is the owner of key generation and encapsulation procedure. So she can use her keypad to establish multiple shared session keys. So the attacker Bob has a capability to construct the ciphertext of his choice and query the decapsulation procedure of the Kyber. So he can use a side channel methodology to retrieve the secret coefficients. So for the background, if you look detail into the side channel attacks on the decapsulation procedure, it can be broadly classified into two categories. The first one is like target operation dependent attacks, where we focus on a specific operation in the decapsulation procedure to observe the leakage to retrieve the secret coefficients. The advantage of this methodology is like you need only few number of traces to retrieve the entire secret key coefficients. But the difficulty is like you'll have only few point of interest because the operation lasts for only few clock cycles. So it is difficult to mount this attack. The second category of attacks, the target operation independent attacks, where we no need to have substantial knowledge of the operations. The advantage of this method is like you'll get a lot of point of interest. So it is relatively easy to mount this attack. But the problem is you need a lot of queries to retrieve the complete secret key. So the example of this attack is a well-known plain text checking based Oracle attack. So now what we are trying to do is we are trying to mount an attack, which is called parallel PZ Oracle attack that requires lesser number of queries to retrieve the secret coefficients. And also it will be easy to mount because it is target operation independent. So before going into the detail of our attack, let me quickly explain how the decapsulation procedure of Kyber looks. So in Kyber, we present the ciphertext to the decryption model. Then the message M will be decrypted using this secret key SK. Then it will be re-encrypted again to produce a ciphertext TT dash, and a comparison will be made. If the ciphertext matches, then a valid shared session key will be established. If not, a random key will be generated. So it's a well-known F4 transform. So now what we are trying to do is to invoke a side channel based oracle that will give us information about the message bit, whether it is 0 or 1. So what we can do is we can construct the ciphertext such that we will have control over this message bits, whether it is 0 or 1. And based on the information we get, we'll also get information about the secret coefficients. So basically through side channel attacks, we'll get information about the message bit, whether it is 0 or 1. It's like a plain text checking oracle. Since we will get information about a single message bit, now we need to construct ciphertext such that we can get information about the secret coefficient from a single message bit. So to do that, what we can do is we need to fix the message bit at the first location. So we need to make the message bit 0 at all the other location. And the message at the first location should give you information about the secret coefficient. So the ciphertext has two components, U and V. So what we can do is, so the message is decrypted using the operation U times S is subtracted from V. So we can choose u to a constant that u times s will always give you 0 when decrypted. And you can fix v only at the first location such that you can play around v such to retrieve the information about different secret coefficients. So what we observed is when we check the decapsulation module of the Kyber, we found that the decryption, there is a decompression operation at the beginning, which actually results in 208 times, which actually results in a particular pattern. Like it always gives you 208 times some x coefficient, so x constant. So what we did is we tried fixing v to 208 times t, and we have chosen u to 208 such that 208 times the secret coefficient will always give you the message bit 0 and decrypted. So now what we can do is we can just change the value of t and we can get information about the secret coefficient. So there is a paper from Asia Crypt, so where they have proposed using a binary decision tree approach to retrieve the secret key information about the secret key coefficients. We followed a similar procedure. So what we did is like the secret coefficients in Kyber follows a centered binomial distributions. So the distribution of -1, 0, and 1 is more significant than -3 and -2 because they appears more frequently. So we tried recovering the secret coefficient that appears more frequently in a lesser number of queries. So this will minimize the total number of queries to required to retrieve the entire secret key coefficients. So this can be calculated using this equation where qx is the number of queries required to retrieve the secret coefficient x, and P R of x is the probability. It's from centered binomial distribution. Probability of appearance of the secret coefficient x. So now for Kyber 5 and 2, we calculated the recubing to be 2.5625. We also extended the approach to Kyber 768, and here the average number of queries required to retrieve a single secret key coefficient would be 2.3125. So this is a total number of queries required to retrieve all the coefficients. So if you multiply the 5 and 2 with 2.5625, it will give you 1312, which is the total number of queries required to retrieve all the coefficients in the coefficients from Kyber 5 and 2. And similarly for 768 and 1024, you will get like 1776 and 2368 respectively. So the key observations are like we can construct ciphertext such that we'll get the information about the secret key through the message bit m, which we can retrieve through the side channel analysis. So now the natural question arises: we fix the message bit at the first location, so it would be possible also to fix the message bit at a different more than one position, such that like each single bit will give you information about one secret coefficient. So if you fix at two position, it will give you information about two secret key coefficients. So it's like a parallelized attack. So this is how the attack looks. So you present with the ciphertext. Now this time, instead of fixing it to first location, we also can fix it to multiple equations, say 2 or 3, and you can it's on the experimental setup. And then say for the example here, we have given like how to retrieve 2 bits such that it will have 4 classes. So for the binary PC Oracle attack that we had discussed before, we fixed the message with the first location. For that, like we have chosen U to 208. So we can use the same thing for the parallel PC Oracle attack. And the only difference is here, like we, instead of fixing the V only at the first location, we can fix at the P location. The number of the P is a number of secret key coefficient that we need to retrieve parallelly. So now in this example, we fixed at 2 locations. Now with the message bits that we observe at the output, from say here M0, M1 will give you information about the secret coefficients at 2 positions. So the key observation that we made is in case of binary PC Oracle attack, we exploited the centered binomial distribution to construct the binary decision tree. But when we are going for the parallel PC Oracle attack, we observe that this property is not significant anymore. The reason is like the main reason why the number of queries got reduced based on the CBT is the coefficients -3 and -2, it appears less frequently in the secret coefficient polynomial. But when we go for parallel PC Oracle attack, in a particular set, the appearance of -3, -2 significantly increases. So now we cannot rely on the same BDT that we have used for binary piezo oracle attack. So now what we have to do is like we need to reduce the depth of the binary tree such that we can retrieve all the coefficients in a least number of queries. So here is a result. So how we calculate is like we calculate the joint distribution of the appearance of secret coefficients multiplied by the maximum number of queries in a particular set, and that result, and it gives us this graph. So you can clearly see that the after the parallelization factor p is equal to 2, we can see that the binary decision tree that we have proposed based on the minimum depth gives us the lesser average number of queries for a particular set. Now, if we calculate the total cost for key recovery, then if we just increase the parallelization factor, then the number of queries, the average total queries required will be reduced. So it now depends on the experimental setup, like how many parallel bits that you can retrieve. So okay, so this is a very fundamental one. Like I hope like everybody knows this. So we normally do Welch test, t-test to classify the attack traces in side channel analysis. So this is a formula for calculating the t-value, which will give you the point of interest. Then you can use it to generate the filter trace, and you can use it for the analysis. And for binary piezo oracle attack, it is straightforward. So you'll definitely able to classify the attack traces based on the templating phase. But what we did is like we extend the binary piezo oracle based classifier for multi-class classifier, because in case of DNN, you need a lot of traces for profiling. So, but in side channel analysis, our focus is to reduce the number of queries. So what we figured out is that by creating a template for different combination of classes, and by finding the class that give you minimum square error, you can actually find out the class that exactly matches the attack trace. So it's more like running a tournament and find out the winner. And we check for the parallelization factor of p is equal to 10, and we are able to accurately classify all the classes. We did an exhaustive study for p is equal to 10. So here is an example where we tried classifying class 330 and 559. And as you can see, like the template of 339 exactly matches with the attack trace of 330. So now to evaluate the total cost of key recovery, so when we are mounting a side channel analysis attack, you will have two phases. One is profiling and the attack phase. So you have to query the same device with the message key, and you have to collect the trace for the particular class. So here the attacker no needs to have a substantial knowledge of the secret key itself. He can just query with the message bit whether it is 0 and 1. He can just construct the valid ciphertext, and he can construct he can do the profiling. So it is independent of the secret key itself, but you have to do the profiling. So that's the matter. So to do the profiling, it depends on the experimental setup. Say your experimental with the experimental setup we are able to do the profiling with the number of traces traces for the template for t is equal to 5. But it could be further reduced if you have a sophisticated system. So this make us to analyze two categories of scenarios. One is with clone device, another is without clone device. So in the presence of with clone device, you do the profiling completely on a separate device, clone device, and you do only the attack phase on the target device. So by doing this, you can reduce the number of queries required actually. Since you are performing the attack on the clone device, it depends only on the it depends only on the PK. So now just by increase the parallelization factor now, we can just reduce the number of queries. So it is straightforward. But what happens is like when you are performing a template profiling phase on the target device itself, in case if you don't have a clone device, now what happens is like you cannot just increase the parallelization factor. And it depends on the number of attack traces required to do the profiling. So for different T, you need to choose the optimum P to perform the attack. So we performed all our attacks with T is equal to 5, which is our experimental capacity. So this is so now an attacker can choose not to just go for multiple secret key coefficient retrieval. Instead, he just may want to just retrieve a particular number of coefficients, and he can use the LW solver, lattice-based solvers to retrieve other coefficients. So his focus may be just to reduce the security strength. So we use this popular tool from the Asia Crypto Conference, where they have used a leaky LW estimator. We have used the tool to find out the number of coefficients that requires to reduce the security strength of the Kyber to a particular level. As you can see, for 512, we just need 354 coefficients that needs to be retrieved through the side channel analysis such that its security strength will be reduced to 2/32. Similarly for others. Yeah, now if we do the analysis with the focus of reducing the security strength, then the number of queries required is even less. So it's just span around some 200 to 600 traces. So now we have two scenarios. So with the clone device, if we just increase the parallelization factor P, it will just reduce the total number of queries required. And we can see, like, if the attacker is arbitrarily able to mount an attack with the parallelization factor of 32, then it will just reduce to two number factors like 72 and 6345. It's very less. And without clone device, you have to do the profiling on the same device. So now for the case like T is equal to 5, we found the optimum to be P is equal to 4. And that time, like, the full key recovery for the Kyber 768 can be done at 613 queries, which is also very less, because for the binary PZ Oracle attacks, you need thousands of traces. So what we also did is we extended our attacks to lightly protected implementations of Kyber with shuffling countermeasures on encoding and decoding operations. Since we are targeting a decapsulation procedure, it's on decoding module. And we tried mounting our attack, but since our attack is independent on the target operation, especially decoding operation doesn't have any major role, we're able to classify the attack traces. So here is an example with class 3, 9, and 7, and 4000 with shuffling automation. So to conclude, we have presented a parallel PZ Oracle attack, which can be used to retrieve multiple secret coefficients parallelly. And we have also presented the binary decision tree that can be used to minimize the number of queries required. And so our experimental setup, we proved, like, with P is equal to 10, we are able to classify accurately using the proposed multi-class classifier. And we validated with the compared to the binary PZ Oracle attack, our attack improves by the factor of 2.89 in case of T is equal to 5 and P is equal to 4. And in the presence of clone device, it even get worse. The number of queries required is reduced by a factor of 7.65. We also discussed a case with presence of clone device and absence of clone device. And with the presence of clone device, the attack is very easy to mount also. So the fundamental takeaway from our work is, like, we need to have a concrete countermeasure like masking. And if in case, so the countermeasure like masking is very expensive. So the designer may choose to go for low-cost countermeasure like shuffling. So in that case, like, our methodology will be used to find the key refresh rate such that, like, in case the ephemeral key setting is not possible. So that's a very useful application of our methodology. Thank you.
So do we have questions? Okay.
Yep. Hello. Thank you very much for the talk, by the way. So I would like to ask, instead of doing a binary classification like a tournament, is it possible to do like a multi-value classification like in one shot? Instead of doing a binary classification, so binary classification tournament, is it possible to do a multi-value or multi-class classification in one shot?
Actually, it is possible. It is possible. Like, you can do a multi-class classification also. It is possible. So we just want to give an example like how it can be done. But compared to DNN, like, we no need to stick with the DNN for the approach, because, like, the traditional template matching itself is giving you the better results. So that's the idea we want to convey through the experiments.
Do we have other questions? Okay, so someone thinking a question. So for the experimental part, you said that yours was like multi-process, like parallelization. So what was the exactly number when you run? Like how many like how many cores in parallel that you use. I see like 10, but it was this in the experimentation, or was like you use other values to see it? And like for the experimental part, you're using like the parallelism, right? And how big did you really go in the experimental part?
So we check for the parallelization factor of p is equal to 10, which means like you can extract 10 bits of 10 secret key coefficients parallelly from the messages. So we did for p is equal to 10. We also check for p is equal to 12, but we randomly picked the samples and checked. It worked in p is equal to 12 also, but we didn't climb the results because we didn't do an exhaustive search for them.
Okay. We have one question from Zoom, so we will just read.
Yeah.
What else countermeasures are not effective to this attack?
Okay, so the main countermeasure that will not be effective is the shuffling. But for the re-encryption, other than masking, to my knowledge, there is no other countermeasure. So so our attack can be mounted if there is no masking, our attack can be mounted on anything.
Okay.
Because it exploits the entire re-encryption procedure for the point of interest. The leakage will be high.
Okay, thank you. Kartik, do you have any other question online or? Okay, Kartik didn't reply. Do we have any other question here? So let's just take the speaker. And we are going to the next talk. So just a minute. Let me get it. I think. Well, I can just also control. It's not a problem. So we are going to our next talk, which is exploiting intermediate value leakage in the lithium, a template-based approach, and the talk is from Anderson. And the clicker is not.
Oh, yeah.
Yeah. Now we have a clicker. Yeah.
Okay, so thank you for the introduction. Good morning, everybody. For this talk, I will be presenting a joint work with Alexandre Berzati, Maya Chartouni, Steven Madec, Damien Vergniaud, and David Vigeland about how to exploit an intermediate value leakage in the lithium through a template-based attack in order to recover the secret key. Okay, so first, I will present the context and motivation behind this work, as well as detailing the scheme that we analyzed. And after that, I will guide you through the different steps of the attack that we introduced in our paper. And in the end, that we will conclude briefly with a discussion about countermeasures. Okay, so as you may already know, Shor has shown a quantum algorithm that can break the integer factorization and discrete logarithm problem in polynomial time. So given a powerful enough quantum computer, this means that some standard public key crypto systems are no longer secure. And for this reason, there have been several international initiatives since around 2016 in order to standardize new post-quantum crypto systems. And so once standardized, these new algorithms will need to be implemented securely in a variety of use cases. Among them is MLDSA, which is being standardized right now by the National Institute of Standards and Technology. And it is based on the lithium, which was chosen at the end of 2022 by the NIST. And so here, this work shows how to use a template attack to exploit an intermediate value leakage in the lithium. And so this can also be applied to MLDSA as well. But now you may ask, what is the lithium? So the lithium is a public key signature algorithm. It is based on two hard problems over structured lattices, so module learning with error and module short integer solutions. It has 3 different security levels, as well as 2 different versions, one deterministic and one randomized. And it was designed with a few points in mind. So first, it's very easy to adjust its security levels. It was also designed with the goal to minimize the combined size of the public key and the signature compared to other PQC signature schemes. And lastly, it has already some constant time properties which makes it suitable to be implemented securely against some type of weak side channel attacks. So for all these reasons, it is recommended to be used in most use cases as the new PQC signature algorithm. And so compared to more traditional signature schemes, here, there is no known efficient algorithm, either classical or quantum, that can solve these two problems in less than exponential time. So before presenting the three main algorithms in dilithium, here we will be working with this ring here. So I don't know how to point. Okay, here, where elements are polynomials with degree less than n, and where coefficients are taken modulo this prime number q here. Now, for the key generation algorithm, we first start by sampling a public matrix A together with two small secrets S1 and S2. Then on line 3, we compute the learning with error sample T. We will split this vector into its upper and lower part, T1 and T0, and the public key will be the upper part T1 with the public matrix A, while the secret key will essentially be the two small secrets S1 and S2. So here we can already see that in dilithium, we will be working with vectors of elements in RQ. And so if we take, for example, this vector T here, which has k polynomials, it is often represented as an array where each of the lines represent a polynomial and where each of the boxes on the lines represent one of the n coefficients. So in dilithium, we will be working essentially with vectors of size k or L, which are public parameters that depend on the security level. So now the signature algorithm is based on the Fiat-Shamir-Withers principle. And basically, we start in line 4 by sampling a commitment vector y given a distribution. We multiply it with the public matrix A, and we split this value once again into its upper and lower part. We will use the upper part W1 into an hash function in order to sample the challenge C. This challenge will be part of the signature and will also be used to compute the response Z, line 8. This response will also be returned with the signature if it's under a security range, line 10. Then the lower part of W0 will be used in line 9 to compute the vector R0 that will be used line 10 in a correctness check. And then the last check, line 13, is also there for correctness purpose. So here, one particularity of dilithium that we can see is this while loop. And so it's the rejection sampling loop that, in fact, is just the fact that we are only going to do the steps from line 4 to line 13 over and over again until all the conditions line 10 and 13 are verified. So here, for those of you who are familiar with dilithium, you can already see some differences between specification given here and the one on the Crystal's website or the NIST website. And this is mainly because here we have decided to follow as closely as possible the various implementations of dilithium. And so the main difference is in line 6 here, where we will be computing the upper and lower part W1 and W0 instead of just the upper part. And so this has repercussions later on line 10, 9, and also 12. But again, this is how dilithium is implemented in most of the public available implementations. Now, the verification algorithm is very much simpler in the sense that we are only going to be recomputing a possible W1 vector with only public information. And so if we have the same W1 vector, we can sample the same challenge C. And if the vector Z is under the security range, we accept the signature. So now for the main part of the presentation, our attack. So actually here, the main idea comes from looking at the verification algorithm, and especially at line 2, where this quantity here, will give us a relationship with W1, W0, and C times T0 minus S2. So here, if an attacker knows that for a given coefficient, the value of W0, then we have equation number 1, where all the purple values are known and where we can recover the corresponding coefficient of T0 minus S2. Then what is left to do is to repeat this process for multiple signatures until we have recovered all the k times n coefficients. So note here that in our work and in this presentation, we are only going to be focusing on the case where W0 is equal to 0 for multiple reasons. Now, once we have recovered the entirety of T0 minus S2, if we look back at the key generation algorithm, this gives us an equation that actually allows us to solve for S1. And as it was already shown in the state of the art, S1 is sufficient to forge signatures. So just to summarize quickly here, if for a given coefficient of W0, we know that it's equal to 0, then we can recover the corresponding coefficient of T0 minus S2. Then once we have recovered the entirety of T0 minus S2, we can solve for S1. So we can see that the efficiency of the attack here will greatly depend on how well we can differentiate for W0 equal to 0 or not. But where can we target this value? Actually, if we look at the signature algorithm, we can see already a few places where W0 is used. So we have, for example, here line 6, where we will be inputting W in order to return W0. But there is also line 9, where we will be subtracting W0 with C times S2. And so in this work, we have decided only to focus on the decomposition function line 6, because after analyzing the various C implementations of this function, we found that it had the greatest potential to maximize the value for the leakage, for the 0 value. Okay, so now that we know which operation to target, we will need to distinguish for W0 equal to 0. And as we were planning to work on an open platform with a public implementation of dilithium, the natural choice to exploit this leakage was to use a template. So template attacks are generally considered to be the most powerful type of side channel attacks, and they can be summarized into 4 main steps. So here on the first one, you will need to have a copy of the victim's device, which needs to be as close as possible as the real one on the hardware and software side. Here, for a known secret key, you will record many traces for many messages. Then on the second step, you can only focus on a few carefully chosen points of interest in order to build your template. Note here that you can also check if you have computed correctly your template by verifying if you are able to match for values on your copy of the victim's device. Then the third step is almost identical as the first one, but on the victim side this time. So here for an unknown secret key, you will record many traces for each of the messages in your dataset. Then on the last step, if everything was done correctly and if there is sufficient leakage, you can apply your template and hopefully try to recover for the correct secret value. So in practice, we decided to use the PecuClean implementation of dilithium, which at the time was the latest one available. It is the deterministic dilithium 2 version, but the attack also worked for other versions of dilithium as well as the randomized version of dilithium. For the hardware, we work with a Chip Whisperer Lite, which is an off-the-shelf board used in academic research. It has a 32-bit Cortex M4 and 48 kilobytes of RAM. Now for the side channel part, we use power traces directly acquired on the Chip Whisperer. And for the targeted operation, so it's the decompose. But if we remember, one particularity of dilithium is the use of rejection sampling. So before signing a message, we won't know how many rounds of rejection we will do. So for this reason, we have decided to only work with the first round, either if we return a valid signature or not. And so for the same reason, we decided to only work with the first coefficient of the first polynomial of a W0 vector. Now for the leakage model, here we decided to consider the Hamming weight of each of the 4 different bytes of a W0 coefficient. And so here the goal for the template, it won't necessarily be to distinguish all the W0s equal to 0, but rather than if we distinguish W0 to be 0, then we have to be as sure as possible. So as I said, here we targeted the decompose operation and we had to acquire enough messages to have enough representatives for each of the 9 Hamming weight classes for each of the 4 bytes. And so this took around 18 hours on the standard PCA. Then for each of those messages, we had to acquire the corresponding power trace on the chip whisperer. And this lasted another 24 hours. And so here I have given an example of such power traces directly acquired on the chip whisperer. And maybe for those of you who are the nearest, you can see already a few variability from samples 110 to 130. And if we actually display the results of the ANOVA statistical test, this confirms that there is indeed leakage about each of the 4 different bytes of the W0 value. And so here we have decided to only keep the 5 points, the 5 peaks of the ANOVA as point of interest to build a template. Then on the matching phase, so here to test our template, we decided to collect 10 traces for a message for which we knew that we will have W0 equal to 0, but that we didn't add it to our learning dataset. And so here on the left, we have the results for the 9 different Hamming weight scores for our template for the 2 least significant bytes. And so we can see that the score for Hamming weight equal to 0 is clearly distinguishable from the rest. Then on the right, we have decided to show the evolution of those scores as a function of the number of traces used for the matching. And so we can see that even with 1 trace, we are able to clearly distinguish for the 0 value. So now to assess the results of our template, we decided to compute the false positive rate, which is the number of W0 equal to 0 that we detected, but that in fact weren't equal to 0. And so we found out that it's a little less than 0.1%. And so this means that in average, we will have at most 1 wrong coefficient from the k times n. We also computed the false negative rate, which is the number of W0 really equal to 0 that we didn't detect. And so we found that it's a little less than 0.2%, but this will only mean that we will need to acquire more signatures for the attack. And so to end the evaluation of this template, we decided to assess the results of the template built on the first coefficient on the other coefficients. And so for around the 100 first decompositions, we found the same false positives and false negative results. So here for an attacker, you can only target 1 decompose, build your template here, and then apply it for the other ones. So in our case, you can see that we didn't have too much false positives, but anyway, adding more false positives will add more noise to the equations. And so this will impact the success rate of the attack. On the other hand, adding more false negatives will only mean that we will need to acquire more signatures. So in order to bias our collect of W0s towards false negatives, we introduce this mathematical filter on public values, which is just this confidence interval here in purple. And so in practice, this discarded around 70% of the k times n coefficients where we might not have W0 equal to 0. And so this has a direct impact on the false positives and so on the success rate of the attack. However, we also discarded around 5% of true W0 equal to 0. But again, this will only mean that we will need to acquire more signatures. So now if you have to remember only 1 slide from this presentation, it's this one. First, you will need to have a copy of the victim's device. So here, for a known secret key, you will recall many power traces. And in our case, we use 700K traces to build a template. Then on the victim's device, here for an unknown secret key, you will record many traces for each of the messages in your dataset. And here you can record as little as 1 trace per message. Then you can apply your template and try to detect if for a given coefficient, you have W0 equal to 0 or not. If it's the case, you save this for later. And if it's not, you throw it away. And then you have to repeat these 2 steps until you have recovered all the k times n coefficients where W0 was equal to 0. And so for this, you will need 2.5 million signatures minimum in order to have recovered all the k times n. And so this is needed for the analytical resolution on the next part. Then once you have recovered all these coefficients, you can finally solve for T0 minus S2 with some methods that can handle noise. In our paper, we use the least square method. And if you really have too much noise, you can also use error management techniques. And in our paper, we show how to use the majority vote here. Once you have recovered the correct T0 minus S2, you can finally solve for S1. And with this piece of the secret key, you can forge signatures. So now that I have presented the attack for the countermeasures, here the goal will be to reduce the leakage spots where we use the plain W0 value in the given order. So for this, there are known simple countermeasures. And so we can use shuffling, for example, during the sensitive step, such as the decompose and the subtraction. And so this will mean that in the collect of W0 equal to 0 and the template, we will need to have another step in order to do the resolution. And so the attack will be harder to do. But there are also more powerful type of countermeasures, such as masking when we manipulate the W0. And so in the state of the art, there are already some mask implementations of the decompose function. And in fact, for the subtraction, we can also use those masked implementation of the decompose because there is an alternative representation of R0 that uses the low bits function that in turn uses the decompose function. So now to summarize, in this work on the lithium, we have shown the first exploitation of a zero value leakage on W0 during the signature that in turn allows us to recover for S1 and forged signatures. In our paper, we show that the leakage can indeed be exploited in practice through experimentation, and we also discuss filtering, resolution, and error management techniques for efficiency, and we also highlight simple known countermeasures. So now for future work, we plan on evaluating the impact of noise on the various error management tools that we use in our paper. So thank you very much for your attention, and if you have any questions, I'd be happy to answer them.
Okay, I see two questions, one here and one in the back. So,
hi, thanks also for the presentation. So I had one question, but like that comes in two parts. So my question is, how does your attack adapt to security level 3 and 5? So how does the size of the lattice impact your attack? And also the decompose function is different for level 3 and 5. And have you ever tried it?
Yeah, because so the decompose function won't have the same range in the outputs. So that's what will differ. But for the template part, we can also do the template for security levels 3 and 5. So it will totally be applied. The only difference between our attack for security level 2 and 3 and 5 is that in our paper, we show that for level 2, we can only focus on 2 templates on the least significant bytes because of this interval. But on level 3 and 5, we will have to do the 4 templates.
Okay, thanks.
we have another question. Wow, there you go.
Thank you for the great talk. Yeah, I was wondering, you mentioned that you choose to especially focus on the constant being zeros and try to build templates where you detect 0 against basically everything else.
Yes.
And you mentioned that you did that for several reasons. So I was curious, what are those reasons? And especially I'm curious if there is a trade-off that can be found, because I think that the main issue is that if you get more classes, then you have a lot of more false positives, and it gets very annoying. And then you need to also not just focus on the Hamming rate and so on. But at the same time, it feels like you're depriving yourself of a lot of information when you're doing that. So yeah, I was wondering if you can comment on that, and is there a trade-off basically?
So as you said, this is one of the reasons that we only focus on the 0 value. Because if we will be focusing on other values, we could potentially add too much false positives. And so too much noise to the equations, and this will impact the success rate. But we also have chosen to only focus on the zero value, because when you see the implementations of the decomposed function, essentially it's a modular division. So you will be computing first the quotient and then the remainder. And so you will compute W1, then you will be subtracting W to W1 times 2 gamma 2. And so if you have 0 here, then you will have a great leakage for this operation. So this is why we only focus on the 0 value.
We have another question.
Yeah, thank you. I have one question or two questions. The first is concerning the ANOVA. Is there a reason why you use ANOVA for the POE instead of other?
So first, we used the ANOVA because it was like the closest statistical test to the template that we use. But we also tried to use other statistical tests such as correlation or even SNR. And we had the same leakages, not in the same positions, but we had the same leakages that can be exploited. So you can use either of the statistical tests that you want, and you can exploit this leakage.
Okay, and if I got it very well, for the learning phase, you use 700K traces.
Yes.
And for the exploitation phase, you use 2.5 million.
And so, yeah, so this is a bit tricky to explain. So here, for the learning phase, we use 700K traces to build a template. But then, so for the matching phase, you will need to have all the K times N coefficients where W0 will be equal to 0. And so for this, you will need many signatures. And so for each signature, we used as little as 1 trace. And then the number given here on the right, the 2.5 millions, this is the number of minimal signatures needed to recover all the positions. So for the template, it's just for the learning, 700K, for the matching, between 1 and 10.
Okay, thank you.
Okay, we don't have more time, so thank you.
Thank you very
The
much.
speaker again. And then we go to the third and last presentation, adapting belief propagation to counter shuffling of entities. And it's going to be by Emmanuel.
All right, thanks. I think that's already.
There's another button to come back.
Not working.
Oh, no, it's working.
I have to push a little longer. Okay. Stronger. All right. So, welcome to my talk about adapting belief propagation to counter shuffling of entities. This is joint work of Julius Hermerling, Silvan Streit, Katharina Thieme, and myself, Emanuele Strieder. Let's have a quick peek. No, I destroyed it again. Yeah, no worries. Next slide, I say, probably. Yes, let's peek into the table of contents. Quick settling of the context. Then I will talk about 2 countermeasures which were proposed by Ravi and others, fine shuffling and coarse shuffling. And finally, some concluding words and outlook. Yeah, right, go into the background. We talk about an attack on the inverse entity in the decryption process of Kyber. Yeah, you see here marked in orange the point of attack. The basic idea of our attack is that, or the attack that was published by Hamburg et al. In 2021 on CHES, is that you take side channel measurements of each coefficient in the in the execution of the inverse NTT, put this side channel information into a belief propagation graph, and then hopefully the belief propagation graph will converge to the real values. We assume here simulated leakage, Hamming weight leakage on a microcontroller. The special attack path here on Hamburg and others take was that they don't use any ciphertext, but they choose the ciphertext such that the input vector to the inverse NTT here, yes, that's working, that the input vector to the inverse NTT here at that point is sparse, so that there are a number of zeros which we can choose. This sparseness can be calculated up front, and you only have to calculate it once, so that's easy for an attacker. This sparseness helps with the belief propagation convergence because you have less noise, and therefore the belief propagation can converge easily. So this work was done in 2021, and we built upon that work. This is how a subgraph of the belief propagation graph looks like. You have the typical layers of the inverse NTT. You have blocks of butterflies with the same twiddle factor. And you see, because that's the inverse NTT, we have the small twiddle factor groups on the left side. And if you go on in the deeper layers, the twiddle factor blocks are getting bigger and bigger. That's important for our later attack there. Yes, we simulated the leakage as usually, just taking the Hamming weight of the real value, putting it in a Gaussian distribution, and controlling the noise using sigma. All right, there was a paper in 2020, actually, so 1 year before 2021, which already proposed countermeasures against such a side channel attack. And Ravi and others proposed shuffling countermeasures. And now we ask ourselves the question, is the Hamburg attack still viable if these countermeasures are applied? All right, so let's talk about shuffling. First, I start with fine shuffling. Fine shuffling is the idea of shuffling the inputs and outputs of one butterfly. So that's the reason why it's called fine shuffling. You have, for one butterfly, you have 4 possible states. And if you try to take side channel measurements now, you get, of course, uncertainty which of the inputs is at which position in each butterfly. If you look at, for example, here the inputs, and you don't know which Hamming weight was executed when here, then you have, of course, a chance of 50% that you guessed the right shuffling. What can you do if you have such a setting? You can either try to take the side channel measurements that you have. So taking both measurements, you have 2 measurements of the, for example, the inputs here. And you can either try to mix the Hamming weight distributions that you get, or you try to somehow unshuffle this thing. And that are the 2 possibilities we tried here to analyze this countermeasure. On the left side, you see the first case. You just have 2 measurements, and you have the Hamming weight distribution. So you have some guess where the Hamming weight that you measured is. And you put now both measurements in one distribution and feed this information again back to our belief propagation graph and see if it's converging. That is a simple, straightforward thing you can do. No problem there. And the second thing is that you try to unshuffle the distributions by weighting them differently. And to do that, we had to introduce a new factor node, which is an extension, a slight extension to belief propagation, because this shuffle parameter factor we call omega here is not exactly belief propagation like, because we don't have probabilities for a value, but we have actually an actual weight here. So that's not typical for belief propagation. And the idea is that you, during initialization of belief propagation, put both distributions in a 50-50 weight into the original graph. So these lines indicate the global entity graph here and the normal butterfly node. And then you have this shuffle node, which has a copy of the original distributions here. And during iterations of the belief propagation graph, these distributions here at the original nodes tend to go to a certain direction. And we measure these distributions using the Kalbach-Lieberg divergence with the measured distributions and find out therefore how the nodes were shuffled, and we can push the graph in a certain direction here. So that both possibilities. The first one was mixing the priors, and the second was using this shuffle node. We tested on the original Hamburg attack. And we see here in orange the case of unshuffled measurements. They go up to a sigma of 1.8. And then you see that just putting using this the straightforward way of just mixing distributions, just using mixing distributions goes up to a sigma of 0.9, and with this shuffle node we could push the noise resistance of this attack to a sigma of up to 1.1. Okay, that's fine shuffling. We could still attack the inverse entity, although fine shuffling is applied. Given we used simulated leakage here that we have to say, so real measurements is a little bit different there, noise levels and different noise influences there. Okay, then we looked at coarse shuffling. What is the idea of coarse shuffling? Instead of now shuffling the input and outputs of one butterfly, coarse shuffling has the idea of taking the butterfly and shuffling the butterfly all over the layer. And if you do it all over the place without respect to the twiddle factor blocks, then it's called coarse shuffling. And if you do it only inside the twiddle factor blocks, then it's called coarse block shuffling. And we argue in our paper that if you can observe the intermediate values, for example, load operation of an intermediate value, you can also observe the load operation of a twiddle factor, and therefore you can go easily from coarse shuffling, where the butterfly is shuffled all over the place, to coarse block shuffling by rearranging the measurements you take. To attack coarse shuffling, we had to extend our attacker model. That's indicated here by this split in the layers. We are now assuming not only having leakage of the load operation, but we also assumed leakage of the store operation. How realistic it is, you have to do the experiments for your microcontroller. But we take this assumption here, and if you have store and load operations between each respective layer, you're ending up with somehow a matching problem. You have just one distribution and another distribution, and you have it for all the variable nodes here, and now you try to match these distributions and try to unshuffle the measurements you take. And if you have unshuffled the thing, you can put it back in the original belief propagation graph and try to let it converge. Of course, there will be more noise as in the unshuffled case, because during matching you will do errors. All right. So we see here in colors indicated how such a matching can look like. Or another possibility is this, for example, this setting. But keep in mind that this is only a subgraph and not the whole belief propagation graph here. Yes. what did we try to do? Indicated the store operations and the load operations here. And the first try we was the so-called one-point matching, that you take the mean value of the Hamming weight distributions as an indicator for the distributions, then put them in a matrix, and let the Synchron-Knopp algorithm do his job. Synchron-Knopp is an iteratively algorithm which searches for most likely matches by standardizing and normalizing rows and columns stepwise. And you get at the end, if the rows are summing up to 1 and the columns are summing up to 1, a doubly stochastic matrix there. And this matrix can be used to unshuffle these measurements. We tried that for one-point matching, and we found that this is not the best way to do it. So it was very noisy and the results weren't very promising. But then we thought of, okay, when we think about cross shuffling, the inputs are not shuffled like in fine shuffling. So the inputs and the outputs of a butterfly are loaded and stored in order. So we have some more information than only one measurement, but we have actually for each butterfly, we have 2 measurements, 2 loads and 2 stores. And we now did exactly the same as in one-point matching. We indicated the distribution with their mean because we think they are Gaussian distributed, put them in the Synchron-Knopp algorithm and do the matching process. And actually that worked promising. And let's look at some results there. You see here a table of entropy levels at each variable node of the NTT graph in each layer. Don't worry about the second to the end column, just look at the first column first. We have here a sigma of 0.1, and we have in the third row the line no shuffling. That are the entropy results during an unshuffled attack, so 8.69. And you see that with 2-point matching, we can quite good reach this entropy level again in the first 4 layers, I would say. And in the later layers, I said before that the twiddle factor blocks are getting bigger, and therefore you have some inherently some noise there because the matching process is getting worse. So therefore, for the first layers, we are able to pretty good match the measurements again. And you see that this development of having worse results in the sense of entropy during later layers is getting also when you look in the other columns, it's getting worse when you look in the later layers, because you have inherently more noise and therefore the matching gets worse. Okay, but for low noise conditions, this still works. And now let's look at some results. We see that here we have the matching unshuffled case in the Hamburg attack. And as a comparison, the 2-point matching with accompanied belief propagation attack in behind. And you see that we reach here still a sigma of 0.5, although the original attack was 1.3 there, we are still able to attack. But of course, the performance of the Hamburg attack is severely mitigated by these shuffling countermeasures. And what we have to say here is that if you now think of mixing, for example, fine shuffling and coarse shuffling, then of course these analyses don't count anymore. So you have to do another thinking of how can we then unshuffle the thing. All right, then I will quickly talk about some little experimental stuff we did also. When you unmatch these shuffled butterflies, you often have the case that you unshuffle correctly in some parts of the graph and you match wrongly in other parts of the graph. And therefore, our idea was, okay, why don't cluster subgraphs of the entity graph and see if these graphs already are converging. And if these graphs are converging, you have some more information as if you would put everything in one graph and let it do its job. And we see here that this is a subgraph, that are results of a subgraph with only 4 inputs. This is a subgraph with 8 inputs. And we did also experiments which are shown in our publication with 16 inputs. And you see that, of course, the more information you have more noise resistance there. But the interesting part is that they are converging. So you can use subgraphs of these measurements and try to let them converge and get some information from that. Yes, we did experiments, bigger experiments with these subgraph convergence. You see here three heat maps. The first heat map indicates how well we did our unmatching process. The second heat map in the middle indicates how often a subgraph was converging on each variable node. Each variable node can be part of multiple subgraphs, because if you choose different input sizes of a subgraph, you find the same variable node or measurement in multiple subgraphs. And yeah, we just counted how often does a subgraph converge for a variable node, and you have in black the non-converging graphs. Gray is one graph converged, and white indicates that for this variable node multiple subgraphs converged. And the third heat map indicates if the final global graph was converging to the correct values. And you see here that we have a little bit of a, I would say, correlation between how well did our matching in the first heat map, how often did the subgraphs converge in the middle part, and did we finally find the correct values in the global belief propagation graph there. This is not fully thought through, we have to say, but we experimental with this, and that leads me to outlook and conclusion. So we extended the CCA side channel attack of Hamburg and tried to verify proposed shuffling countermeasures of Ravi et al. We have to say, all in all, Ravi's countermeasures shuffling, of course, mitigate the performance of the Hamburg attack severely. We proposed a new shuffle node, which may or may not be used in different contexts. So we have to think about that. Yeah, and we did some analysis of 1- and 2-point matching in which exploits the known structure of the entity here. Yeah, proposed some subgraph convergence, which we will try to focus on in future work. Thank you.
So do we have questions? Yes, we have one.
Hi, thanks for the talk. So I had a small question. Is that typically when we deal with shuffling, we can also exploit the leakage on the permutation itself. So I was wondering how you could apply that to fine shuffling, and I guess you could just initiate the omega with some known value from the leakage.
Yes.
But can you do something similar with your analysis on coarse shuffling?
You mean that we could prime somehow the graph with different omega values and then?
No, I mean, could you exploit the leakage on the permutation itself?
Yeah. You can, of course, try to use this information by setting the omega parameter beforehand. Yeah.
Okay, cool. Thanks.
Yeah.
Do you have any other question?
To extend on that, you can also try to guess it. I mean, you can try to guess permutations there and see if parts are converging then. Of course, yeah.
Don't see any question online. Someone else has a question? Okay, so we guess we have a little bit of extra time. So let's just think. We have a question.
So in the table, you reported the entropy values. Is this entropy of the distribution or guessing entropy, or what is it?
That's the entropy of the distribution.
So how do you know that? So you can have an instance where it converges to a wrong value with overconfidence, and that has
Yes.
a low entropy. So how do you know that? Or did you look at other metrics, and how did you know
No,
that it wasn't?
we haven't looked in. Therefore, you mean subgraph convergence now, or
Yeah.
yeah. Therefore, I said it's a little bit of experimental. You don't have. We knew it, but there is no measure that an attacker can use here. Yeah.
Okay.
Yeah.
We have another question.
Thank you for the talk. I was just wondering if you have to assume the graph topology and if your results would still be valid for higher Radix implementations.
Oh, I didn't get the question. Sorry. Can you repeat, please?
If you're computing the entity with any other topology,
Yes.
and if your butterfly could handle higher Radix for inputs, for outputs.
Yes, we didn't look in it, but in principle, if you have that's typical for belief propagation, that if you have information about the variable nodes, which you can also get from different topologies, and you can build an entity which matches this topology, then of course you can use also this attack. But keep in mind that we are here using things like, okay, output nodes are loaded in order and such things. So this is quite exactly a match of that what is done in the algorithm, especially if you think of then shuffling not only on the inside a layer, but also the layers, and you have to recalculate twiddle factors, then it gets more hard. It gets harder and harder, of course. Yeah. So to build an appropriate belief propagation graph.
We have one, like, we still have like time for questions. So, okay, I don't see any question. Let's just thank you all the speaker and all the speakers of the session. Thank you. Thank you. Right.